day 13 and Unit 5, and you start on page 38 in your packet. And you might need highlighters and markers because I'll do a fair amount of highlighting and annotation on these graphs. So the essential question for today is, can I connect and justify features across the graphs of f, f prime, and f double prime? So we're going to bring in everything we know about the function and the characteristics of the first and second derivative to be able to connect and justify features of the graph. And so let's say we're given the graph of the function here. And first thing we can notice about the function is it has some mins and some maxes. And we know at those locations the derivative is 0. And so let's make some connections here then to the first derivative. So if the first derivative, the slopes, so to speak, at the min and the max are 0, the tangent lines are horizontal, then we know if we graph the first derivative that we have 0 values at these locations A and B. So we would have a 0 value or something in the x-axis here. And then let's take a look then. So we know that when we talk about having a relative maximum here, so we're talking about this one right here. We're talking about having being at this top of this hill. We go on a function, we go from an increasing to a decreasing scenario. And of course, increasing means the first derivative is positive, and decreasing means the first derivative is negative. So we know that we have a maximum when the first derivative is equal to 0 and the first derivative changes from positive to negative. So increasing to decreasing. And if we have a minimum down here, then we know again the first derivative is 0 and the first derivative changes from negative to positive. So at this minimum here, we go from decreasing to increasing. So we go from a negative derivative to a positive derivative. And so if you notice talking about maximums and minimums, it's not enough to say that the first derivative is 0. We have to qualify the value of the first derivative is doing on either side of that hill or that valley. So if we take a look then, like I said, we have a decreasing situation here. We have a negative tangent line, a tangent line with negative slope. And so we have a decreasing function here. And what that looks like on the first derivative is we see these negative values here. If we're graphing the values of the first derivative on this graph here, and this is the horizontal axis, then we have negative values below and positive values above, kind of like looking in the fourth and the first quadrant. So we know that if we have the first derivative only, that we can determine some of the features of the graph of the actual function just by looking at what values we have for the first derivative. So if we have the first derivative, we have values that are negative here, we know the function is decreasing, and that correlates to this location on the function. If we know that, on the function here, we see that it's increasing, so we know it has positive slope between A and B. So we're going to expect to see positive derivative values between A and B. So if we notice we start with a 0 derivative at A, then we have positive slopes, then we have a 0 derivative at B. So we start with a 0 derivative value at A, we've got these positive slopes, and then we have a 0 derivative at B. So these slopes must get steeper and then flatter in this domain here. And so we know that the function is increasing. Like if all we had was the derivative, then in this region here with the positive derivative values, we know that we have an increasing function in that domain. And then similarly to the first portion of this graph here, where we have this decreasing function here, we have negative tangent lines with negative slopes. We would expect to see negative derivative values on the derivative graph. So that is connecting f to f prime. And we really, if this is all we have, if all we have is the function, we really can't tell anything about f double prime. We really don't fill in this until we start talking about having this information. And then we can kind of talk about the function and the second derivative. So we really kind of are not going to fill in that column of that table. Okay, so let's say we are given the graph of f double prime here. And let's say we want to talk about some concavity and points of inflection. So if we notice that we have f prime here, and we notice that f prime itself is increasing from from this beginning point here up to location C. So if we notice the derivative here itself is increasing, in other words, if we would draw tangent lines here, they would have positive slope. And if we're drawing tangent lines on the derivative graph, we're talking about the derivative of the derivative, which is the second derivative. So we see here that we have positive second derivative values, and that correlates to an increasing first derivative. So if we notice then here from the beginning of the graph to point C, we know that when we have a positive second derivative, we have a concave up scenario. So we can see that just by having this information, just by having the information about the first derivative, we can see that the first derivative is increasing, which means we have positive second derivatives. And if we have positive second derivatives, that means we have a concave up scenario on the actual function. So what does concave up look like on the first derivative graph? It looks like an increasing scenario. Looks like when the first derivative is increasing. How does it look on the second derivative graph? It's when we have positive second derivative values. So in other words, values that are up here in quadrants 1 and 2. Let's take a look at a concave down scenario. So a concave down scenario is when we have the first derivative decreasing. So we know that the first derivative decreasing means that we have negative tangent lines that have negative slopes. But the tangent lines on the first derivative is a derivative of the first derivative. So that means we have a negative second derivative value, which means we have values down here in quadrants 4 and possibly quadrant 3, if we're just below the x-axis here. And that's going to correlate to this curvature here on the actual function, concave down. So decreasing, so concave down on that first derivative graph looks like a decreasing characteristic on the first derivative graph. So we see the first derivative decreasing. The first derivative decreasing is also going to correlate on the second derivative graph to negative derivative values, because these are the slopes of the tangent lines, which means it's the derivative of the first derivative, which is the second derivative. And having a negative second derivative means we have a concave down scenario on the actual function. Let's talk about points of inflection. So we know points of inflection is when the concavity changes. So we know we have a point of inflection right there, and that's going to correlate to I'm going to call this a hill here, the hill of the first derivative graph. So we know we have a possible, I'm going to use the word possible here, possible point of inflection when the second derivative is 0. Right? And we know that the second derivative is 0 when we have a horizontal tangent on the first derivative, because this tangent line is the derivative of this, which means it's the second derivative of the original function. And so, but that's just a possible point of inflection. We confirm the point of inflection if we change from concave up to concave down, which or vice versa, which we do, because we can see that on the first derivative graph because we change from increasing to decreasing. So we know we have a point of inflection here at C because we change our concavity, and in this case we change it from concave up to concave down. So we're looking on the second derivative graph, we're looking for a second derivative of 0, and then remember this is the big and, right? The second derivative changing sign. So we can see on a second derivative graph that we change signs from positive to negative. So we know this is a point of inflection right here at location C. So a lot of times what we do then is we refer to points of inflection as extreme values of the first derivative. Well, let's kind of digest that phrase. We know that extrema are maxes and mins, and this is on an open interval. So they're local maxes and local mins. So this is an extreme value. This is a local max on the derivative. Okay, so if we have a local max, that means we're changing from positive to negative. If we had a local min, it would mean we're changing from negative to positive. Either way, we're changing signs. So a lot of times we refer to a point of inflection as an extreme value of the first derivative. So the first derivative has a min, let's just say min, not mix. Change that to an n. A min, excuse me, change that to an a max. To be max or a min. So in this case, the first derivative has a max. Okay, so you try these. Notice that in these two questions, I've given you both the graph of the first derivative. So I'm going to back up the screen here for a second. So we're in this scenario where we have the first derivative here. Okay, and I'm asking you questions based off of this graph. Okay, so go ahead and try these and then resume the video after you've tried these. Okay, so if you resume the video, I've assumed you've tried these. So question 1 says the graph of the first derivative is shown. On which intervals is the function increasing? So we know that an increasing function means the first derivative is greater than 0, is positive. So when we talk about having the first derivative and we're talking about positives and negatives, what we're talking about is taking this horizontal axis and I'm saying, hey, up here is positive, down here is negative. So the domains on which the first derivative is positive is this domain here and this domain here. So it looks like it's from -3 to 2 and 5 to infinity. That the function f of x is increasing. And so the answer then, we have to justify these as we answer them. So the answer is that the function is increasing on those intervals, -3 to 2 and 5 to infinity. And then the justification is is this reason right here, because the first derivative is greater than 0 or is positive. All right, question 2, we're looking at this again. We have the graph of the first derivative. So actually, before I answer question 2, kind of observe the fact that when I give you the first derivative, we can draw conclusions about the characteristics of f of x. And when I give you the first derivative, we can draw characteristics about points of inflection, which would be f double prime. We can kind of back off one and go forward one into our graphs. Okay, so the graph of the derivative is shown. At what x values does f have a point of inflection? So we know that a point of inflection has 2 criteria. We got to find where the second derivative is equal to 0 and, big and, where it changes sign. So the second derivative equals 0 and changes sign. So remember, we're looking at the first derivative. So we know that points of inflections are extreme values of the first derivative. Okay, and so this means that we're looking for mins and maxes of the first derivative. It means we're looking for where the slopes change from positive to negative and negative to positive. So here the slopes are positive, and here the slopes are negative. So right at this location where we have a local extrema, a local max of the first derivative, we have a point of inflection because our slopes, which is our second derivative, changes from positive to negative. And down here, we have a local min of our first derivative. So we have another extrema of the first derivative. And we have a change from negative slopes, which means negative second derivative, to positive slopes, which means positive second derivative. So we have a point of inflection right at this location as well. So we say f of x has a point of inflection at x equals 1 and at x equals 3. And then the justification is because f of x, f double prime of x changes sign there. So we can, this justification, we have a little bit of leeway. We can say f double prime changes sign. We could handle them individually, saying this goes from positive to negative and this goes from negative to positive. We could talk about the first derivative having an extrema, a local max and a local min. There's a few ways to justify this that would all receive credit. And just to emphasize it again, points of inflection on the first derivative graph are these extrema, because it's where the slope of the first derivative changes signs. Okay, so a couple more to try here. Notice I'm giving you the graph of f double prime of x here, and then I'm giving you the graph of f of x here. So notice I'm giving you two different pieces of information. So go ahead and stop the video and try these two. Okay, so if the video is running, again, I've assumed you've tried these two. Let's take a look at question 3. The graph of f double prime is shown on which intervals is f of x concave down. So we know concave down means that the second derivative is less than 0. Well, we have the second derivative graphed here, which means less than 0 is this portion of the second derivative graph. This is where my second derivative is negative. And so we have two, it looks like we have two separate domains here where the second derivative is negative, from -2 to -1, and from +1 to +2. So the second derivative is concave down on those domains, -2 to -1 and 1 to 2. And then the justification is we're going to pull right from this definition of concave down because the second derivative is negative. Looking at question 4, the graph of f of x is shown on which intervals is f prime of x increasing. So we know that means that, so notice I'm asking you about the derivative. Where's the derivative increasing? Okay, so this means that the slopes of the derivative are getting bigger, right? This means that if the first derivative is increasing, that means we have an increasing characteristic on the first derivative graph, which means we have the first derivative values getting bigger. And so that means that the second derivative, or the slopes of the first derivative, are positive. Well, where the second derivative is positive, that means the actual function is concave up. So we got to kind of connect it. I'm up here in this upper right-hand portion of the display. We're kind of connecting the dots here from this verbiage increasing to getting to some sort of characteristic of the actual function that we can look at. So where is, if we have the actual function here, where is this function concave up? And it's concave up starting, let's call that starting at 2 out to infinity. So we know we can make our conclusion then that f prime of x is increasing on 2 to infinity because f double prime is greater than 0 is positive. And or we could actually, instead of saying because f double prime is greater than 0, we could actually connect it back to here, saying, well, this is where our function is concave up. So that would be another way to justify that. Okay, so which one is which? So sometimes they give you all three graphs all together on one coordinate plane. And so this gets to be kind of, I kind of call it spaghetti because they kind of get all tangled up with one another here. So it's tough to look at, but we've got to really sort out kind of what we see here. And the best way to sort these things out is to start to look for extreme values on each one of these graphs. So we have the graph that says the graph of the function, its first derivative f prime, and its second derivative f double prime are shown below. Determine which one is which. And so, like I said, we should start looking at extreme values because if we look at extrema, which is where mins and maxes occur, then we know that the derivative has got to have a 0 value there. So let's take a look at the red one. It seems to have the most hills and valleys. So we have an extrema right here, and we have an extrema right here. So I'm going to bring those points down to the axis. and look for which one has a 0 value. And if you notice, blue has a 0 value at both those locations. So we can conclude that blue must be the derivative of red. And so that's kind of our first step. We know that blue is the derivative of red. And so now let's take a look at, let's see, it looks like function blue has an extreme down here. And so I'm going to mark that and bring that up to the axis. And so we notice that the function that has a 0 value at this location, it's like, between 1 and 2 here, is the green function. So if green has a 0 value where blue has a value, then green must be the derivative of blue. So we have blue being the derivative of red and green the derivative of blue. That must mean red must be the function. So red must be f of x, blue must be f prime of x, and green being its derivative must be f double prime of x. So focusing on those mins and maxes really kind of helps us determine which one is which. Okay, when we get back into the classroom, we'll take a look at the takeaways from taking the notes, and we'll move on to our activity.